Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B position, velocity and acceleration practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe, it really helps our channel. So today's problem is divided into two parts. I'm just gonna read part one, but please do make sure that you hit the pause button in order to copy the entire problem. We're actually gonna solve everything. So the first part is, Tommy throws a ball horizontally off a 490 meters tall building at a speed of 8 meters per second. Assume air resistance is negligible and remember to use G is equal to 9.8. Part 1 is, how long will it take for the ball to hit the ground and what is the horizontal distance traveled? So as you can see, I have everything written down here in my notes. So I have, the basic sketch. So it's just one building, 490 meters. I have a little list over here that I'm going to explain in a second. And basically, I think that everybody knows from intuition that if you just launch a ball like this, we're just going to have this parabolic throw, right? And then we're just going to hit the ground somewhere in here. Now, if we split this into travel distance in the x component, then we traveled a certain distance horizontally. And we also travel a certain distance vertically. But the first thing that I'm gonna note over here, and this is, a very common mistake, is that yes, this height is 490 meters, but when it comes to delta y, final minus initial, it really doesn't matter where you're saying y is equal to 0, but you travel 490 meters down. So this is negative 490. The ball went from up to down, so you went down 490 meters. Negative. Okay, so the two things that we have to figure out is, first of all, how long will it take the ball to hit the ground? So what is the time from here to here? And then second of all, what is the horizontal distance traveled? So what is this number? So I have this little chart over here because whenever I have problems that have x and y components and I'm using my kinematic equations, I really like separating completely my problem into x and y. The way in which I like to solve these problems is I make a little table and then I write all of the information that I have about the problem, and once I have done that, then it's sort of very easy to figure out what you have to do. It is a little bit of an extra step, but it's just something that I really like doing because, I'm just gonna go ahead and do it and then I'll just show you why this is very useful. So let's just go ahead and start by figuring out what we know. We do know the acceleration on y because the ball, is not being pushed in any direction by anybody but gravity once it's being thrown. So acceleration is going to be equal to just gravity, which in this case the problem is being very specific that they want us to use 9.8. However, again, in this kinematic equations problems, direction matters. So acceleration on y is actually negative 9.8. If I had this as a positive, then my equations would think that gravity is going up, when in reality gravity is going down. So that part is important. I do have an acceleration on x because nothing is pushing the ball horizontally. Once the ball has left Tommy's hand, the problem says ignore air friction. So we're just gonna head and do that, and that basically means that this is 0. We do have an initial velocity on x and y because the initial velocity is 8 meters per second, but it is completely horizontal, which means that the initial velocity on x is equal to 8 meters per second. The initial velocity on y is 0 meters per second. We don't really have the final velocity for any of this, so I'm just gonna go ahead and skip that. We don't have a travel distance horizontally, obviously that's what we have to find, but we do have delta y, which is negative 490 meters. And of course, this guy is the same for both of them, and we have either. So, so this is the information that we have. And this is why I really like to make this little table. First of all, because if you have everything completely separated, once you're actually using your kinematic equations, you're not gonna confuse values. So what happens a lot is that if people don't do something like this, they might be using a kinematic equation for y, but then just take this number and then just be like, oh, okay, it's 8. I'm just gonna put that number. And that is not true, because the initial velocity for y is 0, not 8. So I just like it because, well, at least I know that I do get very confused if I don't do it this way. Also, it is a very visual tool because out of the 5 things, you can see how many you have. And right away, I can see that I have more things to work with on the y kinematic equations. So if I'm gonna find delta t, I'm definitely gonna have a way easier time using the y kinematic equations. So it is just very obvious to me at this point in the problem that I have to start with the y kinematic equations, versus if I didn't have any sort of visual tool, I really wouldn't know, very well how to start, and maybe I would get stuck. So let's go ahead and look at our kinematic equations. So I already said that I was going to start with y, so now I basically have to pick one of this. I have to work with what I have, and I have to pick one that has what I want. So in this case, what I want to find more than anything is delta t, because the problem is not really asking me for this velocity. So if I don't need to get it, then why would I? So out of these 4 equations, only 3 of them have delta t. And I also need to work with what I actually have, which means that this one has b final. So I don't really have b final. So if I use this equation, I have 2 things that I don't know, so I would get stuck. This one, same thing, it has a b final. So if I use this equation, I'm gonna get stuck again because it's 2 things that I don't know. So my list of information is telling me that the equation that I should be using is this one over here. And see how easy it is really to just have everything on a list and just being able to just like really visually see what you can do. So let me go ahead and write this equation over here. So delta y is equal to by initial delta t plus 1/2 ay delta t squared. All right, so let's just figure out if we can find delta t from here. So delta y is equal to negative 490. This is equal to 0. This is negative 9.8. And this is delta t squared. So this is negative 490 is equal to negative 9.8 divided by 2 delta t squared. My negatives go away, they cancel out. So if I solve, delta t is equal to 2 times 490 divided by 9.8, and then just take a square root. So let's just go ahead and put this on a calculator. So this is 2 times 490 divided by 9.8, and then take a square root, 10. So delta t is equal to 10 seconds, and this is why they wanted 9.8, just to get this very nice exact 10 seconds over here. Alrighty, so now I have my velocity, my delta t, I'm sorry, which is 10 seconds. And please notice that in this case, delta, well, whenever you have these situations, delta t is the same for x and y, because the ball travels simultaneously on the x and the y component. So it takes it 10 seconds to get from here to here, vertically, to travel this vertical distance. It's gonna take it the exact same time to travel this distance horizontally. So by finding this number, I have more information over here on my x table. Okay, so now the next thing that I have to find is So it looks like I'm not gonna find this after all unless the next part of the problem says so, but that's totally fine. I really don't care. The next thing that I need to try to find is delta x. So let's go ahead and see if I can figure this out. So these are my kinematic equations. And first of all, I want delta x. So I'm going to be using either this guy, or this guy. And I don't really have B final. So I think that what I'm going to be using is, this one has B final and this one has B final. So I'm going to be using this one again, except now I'm going to be working on the x component. So let me just copy the equation. All right, so let's see. I'm just gonna substitute the numbers. So delta x is equal to initial x. That would be 8 meters per second. Remember, we're working on x now. Delta t is 10 seconds plus 1/2 acceleration. Oh, acceleration is equal to 0. So this actually, everything cancels out here. So delta x is equal to 80 meters. Ooh, no need for a calculator. There we go. So 80 meters. And that basically solves the first part of our problem. So as you can see, very useful, you know, just have everything very nicely written down here, and it really makes this part easy. But this is not the only part of the problem, so this is actually a very long problem. So let's go ahead and look at the next part. So the next part is, now suppose there is a second building of approximately the same height, but located 25 meters away. The ball is thrown off the first building with the same velocity as part A. The ball will now bounce against the buildings as it falls. Assume the collisions between the ball and the walls happen instantaneously. The figure is not drawn to scale. Okay, so the questions are, if the wall does not affect the vertical component of the ball's velocity at all, how much time will it take for the ball to hit the ground? Okay, well, that's easy. But let's just go ahead and analyze the scenario that we have here. So on the first part, which is, you know, the thing that we just did, there was no building. So this basically, what we calculated was a trajectory that, you know, basically looks something like this, right? But now there is a building. So instead of just continuing the original path, what's gonna happen is that this ball is gonna bounce a couple of times over here. But at this point, I don't really know how many times it is gonna bounce. The first thing that they are asking me to figure out is, if the wall does not affect the vertical component of the ball's velocity, at how much time will it take for the ball to hit the ground? And this one is easy, as I said, because this is just gonna be, again, 10 seconds. And let me explain why. Two things. The problem is explicitly saying that the collisions happen instantaneously. If the collisions happen instantaneously, that means that delta t of the collision is equal to 0, so no time is lost there. But more importantly, delta p is equal to f delta t. So if delta t is equal to 0, delta p is equal to 0. So nothing really changes. This is instantaneous. The wall is not applying any sort of impulse on the ball. So basically, this is exactly the same problem. If the wall is not changing the ball's momentum, if it's not applying any impulse, if it's not changing the trajectory, and again, they again say this on the actual next instructions, the wall is not affecting the vertical component of the ball's velocity. So you essentially have the same problem. So delta t is going to be 10 seconds again. And I think that they just wanted to add this problem, well, this part, just to make you realize, like, hey, even though the situation is a little bit different, if this happens instantaneously, then you know, we have the exact same trajectory, except now we have a bunch of bounces. But let's just go ahead and read the third part of the problem. If the wall changes the direction of the ball's horizontal velocity, again, pay attention, without affecting its magnitude, same thing, how many times will the ball bounce against the walls? Well, okay, so this is where things, you know, we have to go and look at our answer here. So our original distance was 80 meters. So if this building does not exist, the ball would have traveled a total distance of 80 meters before hitting the ground. There is a wall, and even though the bounces are perfect, the ball is still gonna bounce. So the ball is not gonna reach this trajectory. The ball is just gonna stay somewhere in this pit. So let's just go ahead and figure out how many bounces do we have. Well, the ball is gonna travel 25 meters, the first original 25 meters, and then it's gonna hit the wall, and it's gonna have traveled a distance of 25 meters up to this point. Remember, the ball is gonna travel 80 meters with or without this wall. This wall is not changing this because it's not changing it's not putting any sort of impulse over here. So this ball is gonna travel 80 meters, whether it's all the way over here or just bouncing off. So this thing is just gonna bounce, and it's just gonna keep moving over here. And over here, the total there, okay, so this is the first bounce. Delta X, by the time this ball hits the wall a second time, this is 50 meters. And this thing is gonna bounce like this. And delta X3, it's gonna be 75 meters of travel distance. And it was only meant to travel 80 originally, so that means that it's not gonna bounce a fourth time because it only has 5 meters left. So this thing is just gonna fall like this. So final answer is that it will hit the walls exactly 3 times because it was meant to travel 80 meters, and this is 25 meters. So 25, 50, 75, and then it's gonna be 5 meters over here, right? So this is 5 meters. So 3 bounces. Like this. Again, you do need to read the instructions. They are telling you it changes the horizontal velocity without affecting its magnitude. So this is why this applies, because this doesn't really change delta X. Delta X still needs to add up to 80. So there we go. Okay, so now let's see. Part D is, where will the ball land relative to the left wall? Oh, okay, well, I think I figured that already, because if this need to add up to 80, then this distance is 5 meters, because I travel 75 meters up to this point, so I need 5 meters more. So the ball is basically gonna land over here, 5 meters from the right wall, and then if the entire length of this is 25 and they want the distance relative to the left, then this distance, well, it has to be 20. Yeah, so part D is just, oh, this is not a long quiz after all, so this is 20 meters. There we go. Okay, so now what's next? So for the next part, we need to plot the horizontal position and velocity of the ball. Alright, so let me go ahead and change this. So I do have a graph over here. So let's go ahead and make some graphs. I'm just gonna leave this over here as a reference. So let's see. Our position is basically gonna be, so if this is 0, if this is x is equal to 0 and this is x is equal to 25 meters, then we're basically gonna bounce 0, 25, 0, 25, and then just stop at 20, right? Yeah. So let's just go ahead and figure how this would look on a graph. So let's see. My initial position is going to be at 0 because I started where I said 0 was. And then I'm gonna bounce at 25, so I'm just gonna get here. Now, this has to be a straight line because remember, on the first part of our problem, we figured that acceleration at x has to be equal to 0. When your acceleration is equal to 0, your position is a sloped line. It is not a parabola. So that is how I know that it has to be a straight line. And then it bounces and then it goes back. So I'm just gonna go ahead and, make a zigzag over here. And then it bounces and then it goes back to 25. So there we go. And then it goes a little bit back and then it stays at 20. So I just need it to move to like 20 and then just kind of stay there. Yeah, so it just basically stays there, and that is gonna be my position. So now for velocity, well, velocity is gonna stay constant because again, we know that acceleration is equal to 0, and when your acceleration, when your acceleration is equal to 0, your velocity has to stay constant. So your velocity in magnitude is really not changing. However, when we are graphing this, we do need to be mindful that sometimes the ball is moving to the right and then sometimes the ball is moving to the left. So at the beginning, for this part, the ball is actually moving to the right. So I'm just gonna put it over here at +8, positive being to the right. And then you completely switch directions. So now it's going to be -8. Left, and then it goes right again, so it's just gonna be +8 again, like this, and then it's gonna be -8 for just a little bit, and then we hit the ground, and then once we hit the ground, of course, we're just gonna stay at 0 because we're not moving anymore. So like this. All right, that's good. So at this point, our problem is basically complete. The instructions didn't really tell me to find these times. Should I find them? Well, I guess I could find them. Let's just go ahead and figure this out just so we have a complete answer. I don't think that for this particular quiz we needed to find the exact times, but I mean, what are we doing with our lives if we don't? So let's just go ahead and do that. So I have my kinematic equations over here. And I do have my information, right? So let's see. How do I find out this t over here? Well, delta x from here to here is equal to 25. Delta x is equal to 25. I do have my initial and my final velocities. So what am I gonna do? Let's go ahead and use this guy over here. Yeah, let's just go ahead and use this guy over here. So delta x is equal to bxi delta t plus 1/2 ax delta t. Now this part right here, delta x is equal to 25 meters to the right. Velocity in this part is equal to 8. Delta t is what I'm trying to figure out, plus 1/2 0 delta t, so this cancels out. So delta t is equal to 25 over 8. So let's see. 25 over 8 is equal to 3.125. 3.125. There we go. Okay, so now I guess I can just multiply by 2 because this is very symmetric. So if I just do it again, and I'm just gonna find the same thing, so 6.25 9.375. There we go. And then let's just, oh, and then it hits the ground. I already know the time at which it hits the ground, right? So it's the 10 seconds. I don't really need to do that again. So this is 10 seconds. And there we go. So now we actually have a complete graph. So if you found this content helpful, guys, please make sure to leave a like and subscribe. If you have any questions, do let me know. I am sort of aware of the comments. So if you have any suggestions for any problems that you would like me to solve, please go ahead and, you know, leave them on the comments. I am hearing you and your input is greatly appreciated. This is actually all for you guys. So I'll see you guys in the next video.